But now, without further ado, Daniele Oriti will be talking about seeds of space-time and causality and quantum gravity from an emergent perspective. Please, Daniele.
Thanks, Chris. Thanks for being here. So, yes, let me first give you a bit of the plan of what I want to do and what are the goals, and frame it in a slightly broader perspective as a preliminary. Okay, so I gathered that the metaphysics of quantum gravity beyond space-time is supposed to aim at least in asking what is in quantum gravity, what is down there fundamentally. Beyond space-time, because in many of our best models, in different ways, space and time are emergent. So I'm going to discuss this from a certain perspective, and necessarily I have to discuss how usual space-time notions, and also there I'll try to be a bit more specific, emerge from the other structures we start from. But then the main point will be to try to emphasize at this more fundamental level what are the initial starting ingredients that technically at least, and possibly from a more ontological perspective, play the role of seeds for the space-time structures that should emerge in some approximation. And this comes with the general question of whether metaphysics is even possible without space and time, and how it could be grounded within a theory of quantum gravity where space and time are not fundamental. Okay, in particular, we'll touch on the issue of how these seeds can ground laws of nature. Okay, let me start. There is a possible linguistic confusion, at least the one that to a poor physicist looks like often a linguistic confusion. You can say, well, but if you find this particular seed of space-time, this particular feature down there, or this other particular feature, well, that's space-time. And then there's no real emergence on. For me, that's just, let's agree on the choice of words. There is something there which is not what we normally use up there. Call space-time whatever you like. Something up there is emergent from something down there. Name, I don't really care. I can propose a number of funny names for what is down there.
Go ahead.
Don't challenge me. I can really do that. Okay, and then a few preliminaries on aspects that I will not touch upon, but that are somehow implicit in my way of understanding the issues and phrasing the issues and addressing partially the issues. So I take a very broadly intended naturalist perspective. So I try to infer what counts in metaphysics from the physics, however tentative the physics is. And then I will adopt a methodological realism for a first reason that it simplifies language. I pretend that the structures that I will be talking about that appear in our models are there without necessarily committing fully to a metaphysical realism. I think it's methodologically useful, not just a matter of language. It helps us to actually try to extract as much information as possible from our theories, and so this is the perspective I will adopt. For full disclosure, I tend to sympathize with something that could be called participatory or epistemic realism and will need to be fleshed out in much more details, and I would be happy to have your help in fleshing that out, but I will not really discuss that much, just to, as a way of cautionary preliminary remark. What would be crucial is the fact that I definitely distinguish existence or something being real from something being fundamental. Okay, and it will play a role in many parts of the talk. So the main starting point will be that the key elements, the starting elements of our best to be decided theories of quantum gravity are not spatiotemporal in the sense of our best models of space and time physics, being GR and modified theories of gravity in the same language. And by the way, I'm using emergence in the sense of robustness and novelty, and that has been already discussed earlier. Okay, another preliminary remark. I'm going to deal with formal quantum gravity formalism that to a large extent take for granted and directly apply standard quantum mechanical formalism, and do not really immediately question or ask about the interpretation of that formalism. So I take the usual, any of the many formulations of quantum mechanics, Hilbert space and operators, algebras of observables and representations of that algebra, whatever is your preferred formulation, but then take it for granted. Of course, ontological issues in quantum gravity are tied to more general issues about quantum ontology in the foundations of quantum mechanics and the proper interpretation. And you can have your own options about what is actually real in quantum mechanics, if it is the quantum states, the systems to which we associate observables, both of them, neither of them. Okay, I'm not going to discuss that. I have my preference. It will not enter directly what I'm going to talk about. The point is that whatever the precise formulation, for the sake of the rest of the talk, you have to accept, we have to assume that you can have some ontology, therefore some quantum ontology, not directly based on space-time. Okay, because again, space-time doesn't feature there prominently. Okay. Done with the preliminaries. Now let's start discussing. First of all, I try to define a little bit better my terminology. What do I call space-time? What is the thing that is not at the more fundamental level? So yeah, space-time as we know it. And then let me now say how I know it. Okay, now in fact, space and time, one main difficulty, as it was apparent from many of the previous talks, is not so much that the terminology is unclear, but they're very complex notions. There are many things that concur to our understanding of space-time physics and what we actually mean by space-time and related issues. So, and I just made a list. All of them, in different ways, disappear or are not framed in the usual language at the more fundamental levels in the models I'm going to talk about. And all of them, to different degrees of success, have some seeds, some initial ingredient that you can trace back to the more fundamental level, trace down to the more fundamental level. So localization is an aspect that we attribute to what we mean by space and time. That is the very identification of events that are normally local in space and time. Contiguity, which basically is the basis of topology. Contiguity between events and therefore the resulting global topological structure of our space-time. The dimension that was discussed in previous talks, and then extension in temporal or spatial directions, and that is basically geometry, the duration of temporal intervals, length between events in space, separated in space, so geometry. That's what I say geometry, then technically becomes a metric and associated quantities. Then causality is another aspect which is there, and that comes with the signature, the first difference between spatial and temporal directions, at least locally. And then some notion of ordering between events, which is in fact normally a partial order, not a global, total order. Now, all of this has to be part of what we need to reconstruct, because all of them feature in the generativistic theories we currently use to describe space-time physics. Most of the rest is terminology. Okay? So all of this has to be reconstructed somehow, because all of that enters prominently, decisively in the space-time physics we actually do. So we need to reconstruct it. And these are not separated. I mean, this is all about time and space and not immediately and necessarily about causality, but then causality is to a large extent determined once you have a geometry. So these are not, there's a lot of overlaps between these notions. Now, again, space-time as we know it. So what are the ingredients in our space-time theories, meaning generativity? The naive view, sorry for whoever holds it, is that we have a manifold, we have a metric, we have fields defined on the manifolds. Why is it naive? Because you can try to trivialize as much as possible diffeomorphism invariance, but I think that the main consequence of having diffeomorphism invariance, which is not the same as background independence, but they are intertwined, and generativity is background independent because it's a fully dynamical geometry. So in that sense, it's background independent. And then there is a gauge symmetry, which is diffeomorphism invariance, and it's tied to it, because the moment you fix a background, you break the gauge symmetry. The consequence of all of that, to sum up, is that indeed, at the end, the manifold structures beyond the global topological features do not have physical meaning per se. So I'm sorry, the manifold is not space-time. We use it as a mathematical structure to define all the previous notions in terms of fields, but it's not space-time itself. Points on the manifold are not possible events, let alone events. And so on, for the directions, trajectories, and so on. It's a very useful fiction. We use it all the time, and it's perfectly good, but it remains just a tool. So what are space-time observables? You can make the statement and hold the view that they are just global ones. There is a sense in which it's true. They are global with respect to the manifold. But they are, clearly we do local physics, and in order to be consistent with the two statements, local physics is not defined in terms of the manifold if you are rigorous. As an approximation, it works perfectly fine. We use coordinate systems and trajectories and so on. It's all good. That is an approximation. Of what? Local physics, local observables can be defined, but they have to be defined relationally. Global observables is a different story. You don't need any relational description. For local physics, you need to pick up a physical clock, a set of rods, and study the correlations between whatever dynamical entity you want to compute as a function of the values of this clock and rods, which define time and space. These are local when locality is defined with respect to the values of clock and rods. So the simplest example is in the homogeneous case, everything at most with respect to the manifold depends on a temporal parameter, a temporal coordinate. So you may have, I don't know, the Ricci scalar as a function of that. You can have a scalar field as a function of that. The relational strategy tells you that if you're able to do it analytically, you have to invert the temporal coordinate for the scalar field, plug it back inside the other thing, you obtain a diffeomorphism invariant quantity with respect to any time reparameterization, which is in principle a physical full observable of the theory, which is the Ricci scalar at the time defined by the clock value. And this is for time. In the more general case, everything is of course much more complicated, but in principle you do the same globally if you're lucky, locally on the manifold if you're not. You have four scalar fields and they define physical events or points. And then there is a whole issue about what is actually invariant when you choose different physical frames, which I'm not going to touch upon. It's an open and important issue. Okay, of course all of that will reduce to the usual description in terms of coordinates and trajectories on the manifold in the approximation in which your physical clock is ideal. So it basically behaves like a temporal coordinate, and the same is for the rods. Anyway, a lot of physical issues here, but that's just again to clarify what I mean here with some arguments, I hope, about for what I mean by space, time, local structure, and all the rest. Now, this is fully classical. Now, we take a big jump. We look at a class of approaches, class of formalism for quantum gravity, and I try to see what are the type of structures that appear there, and then I try to identify what are the seeds, the ingredients that there either already have a partial interpretation going in the direction of the different space-time structures, or are the seeds on which I rely to extract the continuum, smooth, general-relativistic notions of space, time, causal structure, signature, blah, blah. Okay. These are examples from a broad class of formalism, the one that I know better, which are basically loop quantum gravity on the canonical side, spin forms, group field theories. Now I don't want to enter into the various differences between all this formalism. I'm happy to discuss, but they're not directly crucial. Also, the relation to the causal dynamical triangulations is interesting and useful, but it's not particularly crucial for what I'm going to say in the following. So, the basic mathematical, at least, entities, but if you are a methodological realist to try to take them seriously, are spin networks, at least a complete basis of the fundamental degrees of freedom given by spin networks, which are graphs labeled by algebraic data from SU2 or SL2C, depending on the models. They have a dual sort of equivalent interpretation in terms of polyhedra. So for each vertex of a spin network with, say, n outgoing links, there is a dual picture in terms of a polyhedron with n faces on the boundary. And the tetrahedron is the simplest non-trivial one in 4 dimensions. So now I'm adopting just the 3+1 picture. You can, of course, work in other dimensions. And the gluing of the polyhedra to form extended structures translates into the gluing along links of the vertices to form a graph. All of this is quantum structures because you can associate Hilbert spaces depending on the algebraic degrees of freedom that you put on these combinatorial structures. And they come from quantizing discrete geometry. I don't care now how you actually get to the models. But this is clearly away from the language of a smooth manifold with smooth fields, and that's all I need conceptually from this point onwards. And then I will introduce more. In terms of, these are like spatial structures or boundary structures in your space-time, in your space-time to be. So 1 dimension lower. Then there are, covariant space-time structures which are of this similar type. They are not graphs but complexes, labeled again by algebraic data. So similarly combinatorial and algebraic, and there is a dual representation of the same in terms of quantized simplicial complexes now in 1 dimension higher. The same type of 4 simplices glued together in different ways that were present in Renate's talk. The type of combinatorial structures are similar. Okay. Now, in what sense these already allow you to identify some seeds of geometry and topology? Well, they are expressed, these seeds, in purely combinatorial and algebraic language. That's why I'm not just saying this is space-time stuff. But first of all, you can see a quantum discrete geometry and topology in these quantum gravity states. So first of all, you take a connected graph or a connected simplicial complex in dimension 3, or for the 4-dimensional case, for the 4-dimensional complex, and you can reconstruct, with some effort, I have to admit, a lattice topology out of it. So there is already there a seed of topology. Whether that directly translates into the continuum topology that ends up in the effective relativistic physics description after some limit is to be seen. In particular, it was already discussed, the fact that you're working with something which has the interpretation and the mathematics of 4-dimensional simplicial complexes doesn't guarantee at all that the effective continuum smooth space-time you try to reconstruct will be 4-dimensional, nor that it will be 4-dimensional at all scales in every regime. But you have a seed of a dimension, you have a seed of a topology. In terms of geometry, well, first of all, if you use the SL2C data, you have a notion, you have to believe me because I'm not giving you the mathematics, but you have a notion of phases of the simplicity being time-like or space-like in terms of lattice geometry. And the same for all the lengths, edge lengths, or the normals to simplices and so on. You have a notion at the level of discrete geometry of a local light construction. And again, whether it matches anything in a continuum limit, to be seen. But there is a seed. And then about geometry, well, the same is encoded in the algebraic data that label our quantum states. So you have operators for areas of phases, volumes of simplices, and curvature, and in principle all the lattice geometric operators. Some of them we know very well, others we don't really know, but they are there, at least as a definition. Now, so we have the seeds, and let me emphasize why in this general context we are very far away from the usual space-time and geometry of GR. I just list a number of reasons. Most of them should be already apparent. Generic states, especially in the group field theory case, but you can generalize also in the canonical context, they are not even connected complexes. You can write down states which do not really admit the interpretation of having glued together simplices in a connected, nicely connected way. So we have more general states than that. Of course, we are in the quantum domain. So however nice they are from the point of view of lattice geometry, they are subject to superposition. They're not going to be classical geometries even at the lattice level in any sense. Generic states. Then you have to do some work. In some of the formalism used in these structures, in particular GFT, group field theory, the lattice topology itself is subject to superposition and dynamical. You sum over topologies, for better or worse, because you have the problem of controlling that. It's nice to say, well, the most general possible formalism, but then if you cannot do anything with that, you have a problem. But it's there. It's very different. We have the opposite problem. We have the problem of controlling it, but not the problem of defining a sum over topologies. The same is for geometry. All these quantum geometric data are superposed. A generic state will be a superposition of lattices with highly quantum geometries individually, plus they are superposed. So highly quantum fluctuation in all the operators. The dimension, as I said, they may not coincide with the lattice dimension when you take continuum limits. So all these seeds, moreover, the type of quantum geometries you have, even for a nice connected complex, generically may be degenerate, can have a number of pathologies with respect to metric spaces. When you're super good and super lucky and you're able to control a semi-classical approximation at this discrete level, what you end up with is the sort of things that Renate was discussing. So you can get, at best, at this discrete level, piecewise flat, non-degenerate geometries, which from the continuum point of view, as from the usual space-time point of view, as Renate emphasized, they're very different. They're quite singular. They can be nowhere differentiable. They're definitely not smooth geometries. Okay, I thought that you were... Okay. Okay, now let me do this. So this is just to scare you. Just to tell you, look, we are very far from it. We have a lot of work to do to extract anything, if it was not already clear from all the previous talks. Let me now try to be a little bit more conceptually at least organized from my perspective. What are the steps that we have to take? So, preliminary, so that we understand the various steps, we have to distinguish very carefully, mathematically and conceptually, classical approximation and continuum or collective approximation. They are very different. Of course, the physics we know encoded in GR is both continuum and classical. So we have to get there. Both approximations are needed. But they are conceptually different, and the order in which we take them affects the result. By classical approximation, okay, we just mean that quantum effects become negligible. Now, if you speak with a condensed matter guy and you tell him that means that you send h bar to 0, he will kill you. It is not that. That is at best what a mathematician would do, and a naive mathematician. So first of all, you have to ask classical with respect to which observable. And I give you an example. Take some operator, which casually I named like the area. which is a sum of operators corresponding to components. It receives contributions from some degree of freedom, which together, summed up, give you the total area of some surface. Now you ask, I want to have a semi-classical state with respect to the area. There are two options, and they're different. One is, well, I take a state, which is a coherent state, whatever, wave packet, something semi-classical, but with respect to the individual components. Okay? So it has a minimal h-bar uncertainty on the individual components. And then you sum. The total uncertainty is h-bar times the number of components, because it's an additive extensive operator. Normally what people do if they're interested in minimizing uncertainty into this is they construct coherent states using coherent properties on the microscopic individual component degrees of freedom so that they minimize the uncertainty in the collective observable, not in the individual ones. And then they can have an uncertainty which is h-bar. Even in the conjugate variable can be h-bar, order h-bar. Okay, so a classical limit, first of all, is different from continuum, and I will say a little bit more in a second, but it's also not obvious what you mean by a classical limit if you have a many-body system, something with many degrees of freedom. Now, continuum approximation, I say continuum for simplicity of language, but it just means you have many degrees of freedom. There is a limit in which you include in your description more and more of those degrees of freedom. It's collective physics. If you're dealing with a lattice, well, that's literally a continuum limit. It's a refinement or something like that. But it doesn't have to be exactly in that language. And you can see many examples from molecular physics to hydrodynamics, you name it. In general, okay, it should be clear already that are conceptually different. It's two different type of regimes, which may or may not go together, and definitely not in a simple way, and they are possibly related, but in general, they are non-commutative. I mean, the two limits do not commute. And the obvious example is already, I don't know, quantum fluids. If you take a bunch of atoms, bosonic atoms, and you take first a classical limit of n bosonic atoms, you get n particles, little balls scattering onto one another. Then you take a continuum limit, you get classical hydrodynamics. Of course, it's oversimplified. If you stay quantum and you take a continuum limit, you may use the coherence properties of the atoms to have condensation and BC and superfluidity. And then in a classical limit, you may get standard hydrodynamics when neglecting the quantum potential in the superfluid. But if you invert the two limits, you get a different result. And you may miss physics. You may miss some interesting physics. Anyway, and one can imagine the same for quantum gravity. You have many degrees of freedom, say many spin network-like degrees of freedom. You have to be careful. Do I first take a classical limit and get lattice geometry? And then I take a continuum limit to try to get GR and modifications? Or I just first take some coarse graining continuum approximation, see what I get, and then in case I take a classical limit. Okay. Okay, different levels. Once more, just like I adopted a methodological realism, I will now discuss several steps in which that you have to take in order to get to space-time physics from this more abstract non-spatio-temporal degrees of freedom. Technically, all these steps, I think they're generic. Any approach will have to face those steps, at least at the technical level. So here I'm not necessarily referring to the specific approaches I like or know best. However, the conceptual issues related to the various steps require that you have some ontological commitment to the stories. Otherwise, a lot of these steps will have no conceptual relevance, although they would be still technically needed. Okay. First one, I already discussed that what we actually should mean by space-time physics is the relational rewriting at the classical level of the starting point of classical generativity, fields on a manifold and their correlations. This is already some form of emergence of space-time from a structure that a priori doesn't have a direct physical space-time interpretation, in my view. Then you may quantize. You may think that you have the same type of entities. Your ontology is the same. You have fields. These are your fundamental entities, but you go quantum. All the rest maybe is just technical tools to get there. Then you have another notion of emergence, which is the transition from quantum to classical. If space-time is what we have at the top level, in my definition. However, you may start, and that's the case in these approaches, and from different type of entities, which in the sense I try to clarify, they're non-spatio-temporal. And then you have to do coarse-graining, continuum limits, an extra highly non-trivial set of steps to get to the quantum fields level. Not directly to the classical one, but the quantum one still requires this non-trivial step. From this point of view, the gravitational field and space-time as we know it are the results of collective dynamics. And then there is a bunch of further subtleties, because the continuum limit is never unique. Depending on the parameters, the values of your couplings, you may have different phases, and so the fundamental entities are even less spatio-temporal than you could have imagined, because the same entities, just with different values of the parameter, may lead to phases that do not admit at all the reconstruction of space-time. And then, if you have an ontological commitment and you have different phases, you also have phase transitions, it would be dishonest intellectually to say, well, but I don't have any ontological commitment, I don't try to give physical meaning to the transitions. So there must be some physical meaning from this perspective, and it's interesting to ask what that could be. Okay, so this is the schematic picture. You start from some atoms, something more abstract. You take some continuum collective physics limit. You have a continuum phase diagram with different phases. One, at least, should be geometric, because it seems it's the one we live in. The others we don't know, and there will be transitions between them. From there, we have to reconstruct some quantum generativity, so geometry in terms of fields with the usual type of observables, but quantum, with the relational rewriting to really be sure we are physical. And then we have to take some classical limit. Now, oh, sorry, that's a problem with my ability with Keynote. Now I just flash one example in which you take the various steps within the type of formalism that I discussed in group field theory cosmology. I think is a nice example. Okay, you start from entities, and the basic Hilbert space for those quantized simplices can be given a Fock space structure. So you literally have it at the mathematical level, a quantum many-body system, but with more abstract atoms-like entities. Then you have to choose as an hypothesis in which sort of phase you try to put yourself, what type of collective quantum states you start investigating as somehow plausible candidates for effective continuum physics of a geometric type. So nice suggestion, take a condensate phase and look first at the simplest type of condensate vacuum. This is literally like in a quantum bosonic system. The Gross-Pitaevsky condensate state. Simplest approximation. You're neglecting entanglement between the atoms, you're neglecting a number of quantum correlations, and of course it has limited validity. Then you extract, using these candidate quantum states, an effective continuum hydrodynamic description for these more abstract non-spatiotemporal entities. The dynamical variable is that sigma that enters the state is your collective wave function. In the theory of Bose-Einstein condensates is the Gross-Pitaevsky wave function, the condensate wave function, which you can rewrite in terms of the density of your fluid and the velocity of your fluid. It's a collective variable. And the fact that you use that very simple state is a further approximation. You're not writing down the most general hydrodynamic description for this system of many bodies, but the simplest one. You're neglecting all sorts of quantum corrections. Is mean field aerodynamics. At this stage, you are in a continuum approximation of the theory in one of the phases. You have to do the extra step. You have to rewrite things in terms of observables, and the importance of working with observables, not with other mathematical structures, was emphasized by Renate. You take an observable and you have to rewrite it in a relational language, at least if you want to be consistent with what I said earlier. So at least I have to do it. So in the model, you introduce also some additional seed that should play the role in the limit in the approximation of scalar fields that you want to use as clock and rods, just like you want to take the other algebraic data as seeds for geometry, for the metric and similar. And then you compute observable as a function of this clock value, the clock time. The volume of the universe, you have seen that already earlier, as a function of these clock values is one observable you can compute. And then you have to translate the hydrodynamic equations into equations for such observable. You do that, you have some equation, some complicated equation, and you study if it is interesting or not. And then you can also take a classical approximation. That equation will not be necessarily immediately a generativistic classical dynamics. It may be so in some further approximation, in some regime. And in fact, it turns out that this type of equation you get at large volumes and late clock times looks like the standard Friedmann equation from GR. And at earlier times, it doesn't. It has quantum bounds and all of that. Of course, underlying all of that is the idea that you are in a particular phase and there was some condensation, or there is, at least in the formalism, some phase transition. And then you can try to ask if at this cosmological level there is some signature of that phase transition. Anyway, this is the recap of the story. You start from some theory which is, in a way that I didn't really discuss, is a sum over triangulations with a sum over discrete geometric data, and as I emphasized, the sum over topology is a big mess. But instead of resumming the series explicitly, you take this macroscopic coarse-grained approximation allowed by the field theory description you have, and then you extract physics for observables from the hydrodynamic description. That was the strategy. And then you get some cosmological dynamics through this method. But what the important thing is not so much the results, which are super cool, believe me. The important thing is that you recognize that all the various steps that I mentioned earlier in hopefully full generality are there. And they're all relevant. They're all needed. You're not going to get to this cosmological equation if you didn't take all those steps. Okay, and this was the propaganda slide. Yeah, many cool results, a lot of physics, but this is a metaphysics conference, so I'm not talking about the physics. Okay, but feel free to ask. Okay, actually ask. Now, that's more about the metaphysics. Okay, I told you a bit of the seeds. Let's see if there are more seeds of space and time that we can find. Second, if they can be ground enough for laws of nature. What is the issue? Well, the issue is that the standard account of laws rely in a number of ways on space and time, as has been emphasized by Vincent and Chris. And so there is a tension, there is a problem there. You're not even the chair, but I don't know why I'm looking at you to check. 5 minutes.
Yes.
It's big, so I cannot really fight too much. Okay, anyway, so in humanism, as you know better than I do, laws supervene on a fundamental basis of a distribution of intrinsic properties of physical systems over space-time, facts. And the space-time relations are needed because they're exactly what ties together these otherwise independent, uncorrelated facts. So the question would be, if you don't have space-time, what plays the role, or what could play the role of such gluing relations. This notion is already in tension with the quantum theory, but doesn't matter here. And in other accounts, like primitivism, to cut the story short, because I have now 4 minutes, you need some basic notion of nomic production, which, if you look back at where it comes from, what it entails, it needs some sort of temporal direction, or at least some causal relations. Now, first point, you can at least suggest a notion of new human mosaic, which somehow turns the problem around and says, it's not that the human mosaic is in tension with entanglement in quantum theory, it's that the real basis for a human mosaic understanding of laws, which I don't necessarily endorse, by the way, is entanglement, is the quantum correlations. And in fact, you can find that, and I will skip a good part of the rest, well, you can find that your quantum many-body systems, made of all these quantum tetrahedra or spin network versions and so on, are tied together and form a collective connected structure because they are entangled. It's entanglement between the different building blocks that you reinterpret as gluing connectiveness between them. Moreover, at least for the few examples we control best, a number of geometric quantities can be understood as just measures of entanglement between these building blocks. So the statement is what was earlier. Maybe it is possible to have a different understanding of humanism in the same general scheme, but in a non-spatial temporal context, by actually relying on entanglement as the basic notion. Okay, in primitivism, you need some notion of proto-causal ordering that hopefully grounds nomic production. And in spin forms, or in these quantum simplicial processes that appear as histories, as dynamical interaction processes, it can be found, you can retrace them in terms of quantum causal histories. And I'll cut the story short because I think now I have 1 minute. Yeah, in case you ask, and I'll give you more details. You take the same formulation that I gave in terms of quantum simplicial complexes as histories of all these building blocks interacting. You can look at it a little bit more carefully in a Lorentzian context, so taking advantage of the seeds of local Lorentz structure and light cones that you have. You reinterpret the the connectivity between interaction vertices of these histories as causal relations. You need a simplicial compass which is orientable and in fact oriented, because it's this orientation that you want to reinterpret as a causal, discrete causal relation. You get a partial order. However, it's not like it's not a poset, because in general you also have closed loops, closed time-like loops, closed causal loops. You can then also associate Hilbert spaces, and you can frame the whole dynamics of these lattice path integrals appearing in the processes for the processes of these models in terms of quantum causal histories. So you have a quantum causal history to which you associate an amplitude, a probability amplitude. Okay, and then you have a number. You need, if you really want a proper causal description, you need causal unitary evolution. The whole system should be a quantum circuit. And that requires a number of conditions, which you can impose, but then you have the problem that the moment you superpose all these histories, the resulting superposition may not satisfy the conditions you put on the individual histories. In fact, the generic statement is that, for example, if you have unitarity on the individual history, the sum over them will not be unitary. So the message is just that you can list a number of conditions of a proper causal interpretation. It's non-trivial for your model to implement them. Then you also have this closed time-like loops, which is a problem because you may decide you have several strategies. In general, they are there. And then you can say, well, one possibility is that I modify my model so that I just eliminate them by fiat. They do not appear. I don't know how to do it, but it's a possibility. Well, I don't know how to do it in this context. There are examples that we've seen. Or you can still work with quantum amplitudes that do not eliminate, but simply suppress. They make them smaller, non-dominant configurations. Or you can only allow so-called harmless causal loops from the point of view of quantum information. There are criteria in quantum information for which you may have a closed time-like loop, but it doesn't really constitute an obstacle to a nice transmission of information across the network. And the other problem we have in these models, and so some extra work that we need to do, in fact, the models that exist, most of them, the most studied ones, do not actually register the orientation of the complex, which is the thing that I wanted to interpret as a causal structure, as a partial order. You can modify them. I've been working on that when I was a kid. But the construction ends up being pretty ad hoc. Okay, so you can do that. You can have models that depend on such orientation, so they're more causal than the usual ones, but the construction is a bit ad hoc. Okay, so you can have, in principle, some seed that could ground both laws in a primitivist approach or in a human approach, but you need a lot of extra work, and that requires clarifying the ontology of your theory, at least as a methodological step. Thank you.
Tim Riedel will give us comments about Daniele's talk, please.
Yes, so first of all, thank you, Daniele, for the talk, and thank you in particular for disentangling these different steps, these different levels of space-time emergence. I think I found that very helpful conceptually. I have 3 points to make in my comments. I'm ashamed to say that none of them consist in asking about the physics slide, but I'm sure that the rest of the bunch will rectify that omission during the Q&A. The first thing I want to say, I want to ask you, in fact, pertains to the relationalist strategy, and in particular the notion of relational time. And what I would invite you to elaborate on is what exactly it is, in your view, that justifies calling these parameterizations relational time, or calling these variables that we use to parameterize other variables, clock variables. And I ask it in particular because I read in one of your papers about space-time emergence more generally that you seem to be gesturing towards the possibility that some such notion of relational time may even, in certain very special circumstances, remain applicable during phase transitions, so the transition from non-spatiotemporal to spatiotemporal phases. And that made me wonder what exactly it is that would be required for us to speak of there being some sort of proto-time that would allow us to interpret this sort of transition in a sort of proto-temporal sense. So that would be the first point. The second point also refers to something I read in your papers. You didn't really mention that today, but when I read them, I was struck by the fact that you, when discussing the different levels of space-time emergence, you repeatedly and very decidedly said that one crucial task is to gain new physical intuitions for the nature of the new fundamental entities that we introduce in these approaches to quantum gravity. And I was just a bit curious about that because it got me wondering what exactly you think the role is of these intuitions that you say we need to develop. Because, I mean, a different attitude would be as long as we've got some sort of mathematical control over these entities that seem to pop up in the theories, that's first of all we need, and second of all we can hope to achieve. But what you seem to, what I took you as saying is that there's some more substantive understanding that we may gain for, well, let's say their nature, and that also resonates with your idea that we need to develop a new metaphysics for these regimes. So that would be the second invitation to elaborate a bit further. And the third one finally pertains to the philosophy of laws. While I find it doubtlessly worthwhile to investigate into the fate of the Jungian approach and the sort of productive governing approach to laws of nature, I was a bit surprised that you didn't discuss, neither today nor in the draft or paper about that you didn't discuss another approach to laws of nature that has become comparatively popular, I feel, in recent years in the philosophy literature, which is the notion of laws of nature as constraints. So the idea that laws of nature are, in a sense, governing, but they do govern not in this causal, temporal, productive sense, but simply by constraining the space of physical possibilities. And I thought at first sight that was an approach that carries over very naturally, probably also to a realm where we don't have a spatio-temporal arena. Maybe that's already too naive, but that was my first guess at least. And maybe the fact that with the other two we have to, we seem to be forced to go through these sorts of very impressive gymnastics is indication that we have reason to favor this alternative approach that maybe looks more natural and effortless in that new regime. So these are my 3 points.
Okay, so clock time across the transition. Laws was the third, and the second was why intuition.
Yes.
Okay. So no, not really. I don't think that you need to have some degree of freedom that somehow you follow as a clock, you use as a clock across a transition. You don't have to. In order to extract physical consequences of the existence of a phase transition, I think what we need to have is something more limited, which is a notional clock that you use within the geometric phase, that you whose values you can relate to the G flow, to the movement across phase space up to the critical point representing a transition. That will give an intuition of what the physical meaning of the transition could be, or the physical regime corresponding to the transition could be, from the point of view of the geometric phase. Now, if somehow you can connect that variable to some other variable in the other phase that somehow also leads to the phase transition and you show some relation, that's nice because it allows you to do more, but it will not be a requirement. Okay, an example would be, you have some cosmological interpretation for the macroscopic super approximate evolution within the geometric phase in terms of some scalar field being a clock. If it turns out that in the RG analysis, in the RG flow of the same type of models, you can use that clock as a scale for labeling the different regimes of the RG flow, it may turn out that a specific range of values of that clock is actually at the transition or is approaching the transition. And then you say, well, what is going on is that, I don't know, at small values of the clock time, we are reaching a phase transition which now has a cosmological meaning. Is an hypothesis. But again, this physical interpretation, I think, is first of all needed and possible in the geometric phase. If you can do more, all the better. But I'm not really requiring that there is something going through. Even if there was, the temporal interpretation of this degree of freedom will only be valid in the geometric phase anyway. And then we will have to find some other interpretation in case for the other phase. Okay, that's the first question. So why physical intuition? First of all, it's good to question my own methods and aptitudes, but not that I always can justify them. But the point is that I frankly don't know of any physicist, though they may pretend, that doesn't use some physical intuition. It should be clear that relying on physical intuition is a very weak sense. I don't mean that somehow what we actually find out in our more abstract theories, starting from quantum mechanics, let alone quantum gravity, should match our intuition in everyday life. I mean, I already dropped that pretense when I studied quantum mechanics. So I don't think that's the case. However, having some intuition, even in the form of analogies, can be very useful in getting some ideas of how to proceed, what you have to ask to your theory, what you have to test, which hypothesis you want to test or realize. That's it. That's just that. The third question was about laws. Why didn't I discuss the view of laws as constraints? Okay. In the talk, I think because I finished really preparing it only 2 days ago, and I was already late for sending everything to you. And in fact, you can notice the terrible risk of being so late, and so having to tell your commentator that he cannot rely on your slides just to look at such and such papers. But then he finds in the papers things that you actually are not going to discuss, and you were hoping to leave aside. Okay, so why didn't I? Okay, first of all, even if I want to try to see a correspondent notion of constraints in these models, I would have any way to clarify what sort of seeds are there for space-time in order to find constraints about what. What type of constraints, in concrete terms in this formalism, may play the role of laws. So I don't think it would change much about the global story. Second, because maybe it's a bit too easy, because the dynamics in these models is always in the form of some constraints. Only after all these steps, it may take the form approximately of an evolution equation in terms of some clock. The basic equation is going to be always of the form you have some states, and this is an operator constraint on such states. One form or the other. It doesn't have to be like in canonical quantum gravity, it doesn't have to be a Wheeler-DeWitt type thing, but it's always in the form of a constraint because structurally you don't have time.
Isn't that a great reason to embrace the account of laws as constraints?
Sorry?
Isn't that a great reason to think of laws as constraints?
There is a structural reason for saying that in whatever sense precisely implements dynamics in these models, has the form of a constraint. I'm not saying if it is laws, exactly if you want to take that as being laws, it's a different story. But whatever you mean by dynamics here, because you don't have time, is not going to be an evolution equation. As simple as that. If you take a more path integral intuition of these models, it will be in the form of a set of Schwinger-Dyson equations. And those are constraints for your correlation functions. If you take a more canonical picture, your operators and states, and you look at that, you're going to have operator state equals 0. So it's a constraint. You don't have any time direction to play a role at the fundamental level. So it's always going to be a constraint. Then I will really not know what I'm adding to this when I try to say, well, this could be a law. Yeah, this could be a law, but it doesn't sound particularly interesting to me. Third reason, it didn't really come up when I discussed with Vincent about laws, and so we didn't include it in the paper.
Okay, thank you.
About the role, on one slide you mentioned the role of entanglement. In establishing connectedness. Maybe you could say a little bit about the way about the similarities and differences between the role it plays here and the role entanglement entropy plays when discussed in a stringy context.
Yes, I'm not sure it will be very interesting, but I can say something. Okay. qualitative level is the same idea. It's exactly the same thing. You try to invert the relation. You can say, look, I can find some entanglement relation between the quantum degrees of freedom of a certain system, which I interpret as part of the quantum gravity story, located in different locations, but I invert the relation, and it's the quantum correlation that defines the distance or the connectivity of two regions. It's the same story here. And the same is for other measures of entanglement and geometric aspects like areas and volumes and so on. When you go a little bit more concrete, it's actually very different, because there what they actually compute is not even in string theory, it's normally in the CFT. Then they map to gravitational geometric quantities in the bulk in an ADS CFT context. And here, of course, I'm not dealing with a continuum quantum field theory, it's not a conformal one, and I'm not on a given manifold or boundary of a given manifold, so all the technical differences are very far away. But the spirit is the same, and somehow what we try to do is similar. I was inspired by some of that, and disgusted by some other of that, but...
Thank you. That was very interesting. I was just wondering, because at least when I read Modin and his version of primitivism, like, I have the feeling that he has like this really strong notion of time in the sense of temporal evolution, and it's directed towards only one direction. And so I see what you're doing with the this notion of relational time in quantum gravity approaches, but I think there are two different notions of time, and not any notion of time would guarantee that we can apply a primitivist, at least in a strong primitivist view about laws in non-spatiotemporal, so-called non-spatiotemporal context. So maybe you could.
Okay. On this general topic, I think I have more to learn than to teach. Most topics, in fact. Now, my understanding is that having a notion, some sort of notion of time is only indeed part of the story for non-introduction. What is really needed is really some causal aspect, because the governing aspect is really like a cause-effect relation in one way. It doesn't have to be a spatial-temporal notion, but it's implicitly of that type. It could be a constraint, but that's a different form of governing. And so that's why I try to emphasize that when asking whether there is some ground for primitivism in these models, I was not referring anymore to the fact there is some relational clock that you use, because that is not enough to have any causal aspect. You really need some proto-causal structure in your fundamental degrees of freedom. So I was very fast, but I tried to show that you can understand these models in terms of partial orders. So there is an ordering relation that you can interpret as a primitive aspect of a cause-effect relation, a bit like in causal sets, but in a broader context, because you have Hilbert spaces, because you may have closed Lamarck loops, and for other reasons.
But then when you switched, because you talked also about the cosmological context.
At the beginning, yes.
Yeah. Because then when you switch to the cosmological context, this notion of like evolution is way stronger there.
Well, way stronger, but we also look at the less powerful observables.
Yeah, so there is like this.
We ask a simpler question, which is just we have a notion of volume for the whole universe by adding together the contributions from all the building blocks. And we want to see how it evolves in terms of some notion of time. The only notion that makes sense according to the previous argument is some clock. So we try to rewrite everything in terms of a clock evolution. But notions of causality and similar do not really enter for this observable in this context. And so they are not there.
Emilia.
Right, so thanks Daniele for the presentation. So I was wondering whether you could expand a bit on the part you were discussing on seeds of geometry and topology. And in particular, I would like to hear more about, because it feels to me that there's some kind of role played by top-down considerations, and so you were saying that we may find a Lorentzian signature, and so a local way to distinguish between time-like and space-time seed, let's say, but it looks as if you somehow get it from construction, right? Because you're using SL2C or S2C data, so it shouldn't be surprising that we find this. It doesn't seem to be a genuine. So, I don't know. So it feels like it is a bottom-up approach.
That was not emergent. There was no claim that these seeds are emergent. These are seeds we find when we look at the theory at the fundamental level.
Yeah, but we're imposing to our group structure.
We are constructing the theory. And now I'm saying which of the stuff that I use, which of the ingredients I put to construct the theory, is the one that, to my best understanding, will play the role of seed for the structure, spatio-temporal structure that has to emerge. This is the thing. They are not themselves emergent, and it's not that we find them in the sense that I mean, I can pretend that somebody gives me the theory and I say, oh wow, let me analyze. Oh, this surprisingly I found a seed for causal structure or a seed for topology, a notion of topology nobody was expecting. It requires more work. Of course, I glossed over a number of technical difficulties for doing what I said. But the statement was just that you take these states and there is a way, with a lot of work, to say, look, these states correspond to a certain lattice topology. In this sense, there is a notion, seed of topology in the states, in these structures. You may need more or less work to spell it out, but they are there. It was already there. And it was there because, yes, we constructed as a community the models in a certain way. So that's okay. I don't believe that we find things in nature like that. I mean,
no,
we construct
I was just
theories.
wondering how surprising that could be if that's the way in which you.
No, what is surprising is if that works. What is surprising is that they indeed, according to our initial intuition, do end up playing a good role for the emergence of space, time, causality, and so on. That's the non-trivial part. In many ways, the fact that we have, I don't know, simplices with phases which are time-like or space-like is because we decided to use a certain set of data and because we think that that would be the bare minimum of seeds we need to reconstruct things. Of course, it's no miracle.
I will. Okay. Sorry. Thank you. It was very inspiring, but I might not have understood.
Yeah, me neither.
Okay. Especially on the technicalities. So you were saying that we are talking about emergence, and you accept the definition of emergence that has novelty, autonomy, and dependence.
Yeah, and I just emphasized. I mean, I didn't emphasize now that there's going to be a lot of approximation limits and so on. They're constitutive of the very definition, I think.
Okay, but. In one of the slides, you were giving an example of how this physically is supposed to emerge, of which I might not know
referring to
everything.
Yeah.
But I was wondering whether this is really emergence or not, maybe a derivation, a consequence, where is the novelty?
I believe that emergence is compatible with reduction and with deduction.
Ah, okay.
So I don't believe in any notion of strong emergence, if that's what you have in mind. I only believe in weak emergence, and I think most physicists would side with me there. And in fact, the funny part is that every time you ask for a notion, an example of strong emergence is always consciousness, which is the thing that we least understand. And so I'm not very convinced. Weak emergence as a meaning, I take that sort of characterization of what emergence means, and the statement would simply be concretely realized in the fact that, this sort of equations for something that plays the role and behaves like a volume evolving in time was definitely not in the initial set of states and degrees of freedom and so on. Otherwise, all the steps that we had to take were easy, and believe me, they were not.
Okay, I totally agree, but this is supposed to be also the novelty.
That's the novelty, yes.
Okay.
And the approximations, I can make the list, but there are many approximations and limits. The robustness, I have to admit, we need to check more. I mean, the point is that definitely the resulting equation only depends on some key features of the initial models. So you expect some sort of universality and some robustness of the result. But admittedly, we only looked at one very simple observable in a very specific approximation. How robust is the emergent physics has to be tested.
Can I ask another question?
Yes, sure.
So because we were talking about seeds and presumably
What, sorry?
seeds, right?
Mm-hmm.
And presumably then the evolution of field or the deduction is what comes to the space-time. Are we also at the end of the process understanding the space-time in another way because we got something from the seeds as well? I mean, there are a lot of interpretation of space-time and relativity, whether it's relational, substantialism, or whatever.
Mm-hmm.
Is it something that we also learn from?
Okay, this is something that I definitely hope. Once we have a broader set of observables and results, and we have much more refined picture of the emergent space-time physics, including all the quantum corrections and new effects that we didn't expect coming from the fundamental formulation, then I expect that this will come also with a reassessment of our very understanding of space and time. At this level, assuming that something like that happens, the only thing that I could say is that, well, if it turns out that the whole thing works, with one or another model, one or another fundamental formalism and so on, well, at the very least, what we'll be stating in a realist approach, perspective, will be that, yeah, space and time are in fact emergent, collective notions, non-fundamental, and there is something else which is more fundamental, whose ontology we have to clarify, but definitely will be a new understanding of space and time. It's not the starting point of our intuition, it's not the basis for our physics, there's something else.
Okay.
At the very
And
least.
it would never happen that, for example, we will have to give up on some notion, like for example, locations, this super...
As fundamental,
Yeah.
for sure.
Okay.
As useful, no, because I keep locating the bottle on the table and you up there and receiving signals that I model as propagating locally in space-time within the light cone. So in that sense, no, it's what I was saying at the beginning. Reality is different from, real is different than fundamental. So space and time will be, if all of that works, non-fundamental, but it will not be less real. A river is as real as the molecules. They're just not, one is fundamental, the other not.
Nick.
So thanks. I've heard bits of this talk before. But
It's not that talk, come on, otherwise I would not have prepared this so late.
But one thing you said that I was really interesting, yeah, I mean many things you said were really interesting, which was connecting it up to the causal dynamic of triangulations. I'm kind of hoping Renata might say something sort of as well. So could you say a bit more, and I hate to kind of bring it back to my thoughts there, but to talk a bit about the relation in that way as well. I take it GFT is a theory, a proposal that would, if the world was like that, it would have broader scope than CDT. CDT would be the same physics, but in a particular kind of regime.
You and me and Renate to fight in public? I mean,
I was kind of hoping.
I don't see the point, nor the fight.
Well, but I think it sort of it does go to the question I was asking her as well. Sort of, yeah. In what way is GFT broader? I take it at least in your terms, CDT would be working in the sort of hydrodynamic phase and not in sort of other phases or something like that.
No, okay.
But whatever, yeah. However,
let me
sort of see the relation.
Let me try to clarify what I think here. So if you take the fundamental formulation of GFT models with enough discrete geometric data to have an understanding in terms of discrete geometry, so it's a class of models. What happens is that the partition function of the theory and the amplitudes, the transition amplitudes of the theory can be expressed in a particular regime, in a perturbative regime, as a sum over triangulations with amplitudes which can be recast in the language of a sum over geometric data with a discrete gravity action as a measure. Now, so it's a mathematical fact that this is a generalization of that type of framework. First of all, because the set of configurations, unless you really try hard to exclude them, will be much broader. You have all topologies, you may have all sorts of pathologies there. Even when you go to causal models, is a more general class of Lorentzian structures with possibly more pathologies. So it's just at the mathematical, technical level is a more general framework, and according to one of the two, is a uselessly more general framework. according to the other one, is a potentially useful more general framework. And I want to now put names on to different views. Now, so that's a fact. That's one difference. That comes with, again, depending on the point of view, with a number of extra troubles. From a different point of view, which is true, but from a different point of view, a lot of other tools that you may try to use and guidelines for how to proceed and mathematical structures that you can try to use. Okay,
Can I just ask why perturbative?
Because this expansion in terms of sum over triangulations comes out as the Feynman perturbative expansion of the initial partition function. The triangulations are the Feynman diagrams. So it's in that regime you have this sort of discrete gravity picture.
Okay.
Otherwise,
so, I mean, that equation doesn't look particularly.
No.
Itself,
Well, this is the coupling constant. So this is a series expansion in the coupling constant.
Okay.
So it's a fact that this is a more general way of dealing with the discrete gravity path integral with the sum over triangulations and so on. Useful or not, we can see. Okay, so that's the factor. The other difference, so the first difference is given this, where this is useful or not. The second difference is not so much the fact that there are different phases, the fact that you have a geometric phase that you have to find, and you may have other non-geometric phases. This is true also in causal dynamical triangulations. In fact, the whole point is that they managed, in that context, to find, with respect to some observables, a phase that looks nicely geometric by explicitly resumming the series numerically and evaluating observables, and that's not easy, and it's quite remarkable. But the picture is the same. Depending on the couplings, the values of the couplings, you may have different phases, and you have to identify at least one geometric one. The difference, but that again, I already tried to emphasize that it's not really at the technical level of what you try to do. There are differences there, but they're not the decisive one. They're not very big. It's more whether you interpret these discrete structures just as regulators, and as far as I understand, that's the way they are understood in dynamical triangulations. Or you try at least methodologically, as I emphasized, to take some ontological commitment and ask, okay, maybe they're physical. That changes not so much the story about phases and phase transitions, but what you look for in this story, what you try to achieve, what type of quantities you try to compute. There are a number of practical differences, but they're not so big after all, I think.
Okay, great. No, that's great.
And there's nothing to fight about, I think.
Yeah, thanks. I mean, there are actually many clarificatory questions that I would like to ask, but I will, I guess, try to go a bit more in depth on the relational time in the phase transition, in the sense that I mean, like you say, like it's not. I mean, you don't need to really have a relational time that relates to the geometric phase. You just need like some kind of clock. And like my question is like, why do you need it? In the sense of like, is it because of the initial claim that when you do space-time physics, you should always express stuff in relational terms? Or I mean, like, well, I mean, why do you call it the clock? In this sense.
What time is it?
11.
How do you know?
Well, I check my phone.
Why you call it a clock? You're using it as a clock. You're using it to define what you mean by time. That's the point. You take some scalar degree of freedom. Of course, there are a number of constraints that it has to satisfy. And the simplest example I mentioned earlier, you use as a, you're let's say, safe in interpreting as a clock something that you can invert at least locally for the time coordinate. So in that context, everything is simpler. You have a manifold, you use it, you have fields, everything is much simpler. But at the end of the day, you picked up one scalar field in your set of degrees of freedom that satisfies some decent conditions, and you decide to use it as a clock. And then you have evolution with respect to that. That evolution may be pathological or problematic in a number of ways, and you may find out that the evolution in time so defined is so problematic that maybe you start suspecting you have chosen the wrong clock, or that there was some other reason, some other condition that that clock didn't satisfy that you should have imposed in order not to have a meaningless physics. That's one issue. The other issue is, in general, is not that you have one scalar field in the world, or one scalar degree of freedom. Why you pick up that? And what happens if you pick up another one? I think this is totally open. Not only in my understanding, but I think it's an open issue in general. We do not know exactly what is invariant, if anything, in the physical observables we may compute in different relational deparameterizations, if we use one clock or another. We don't know if there exists necessarily a map between the two descriptions, and we don't know what is invariant between the two. And when I'm talking about truly physical clocks, a truly physical clock has its own dynamics, it back reacts on the geometry, it sees its energy momentum tensor sits at the right-hand side of the Einstein's equations. It's a quantum system, so in fact it's not even just a classical scalar field, it's a quantum system. We only know what happens if all of these features disappear, are negligible, because then the clock, the scalar field, will behave like a coordinate. And then we know that we have general covariance and different invariance and so on. But it's a very idealized approximation. The physical clock changes space-time, it has quantum fluctuations, however small, and so on.
So, like, the idea is we need some parameter that we can use to express the dynamics. So we just...
A clock is the scalar quantity, because it's a number, that you use to label the evolution of the other quantities, that you choose as time. That's an abstract definition. Then in practice, I said, it has to be a scalar field, it has to have some invertibility property with respect to time, it has to work on special solutions for the dynamics of the scalar field, and so on. There are many practical constraints. But the relational perspective is that you define time by a clock, and that's the best definition to have local physics.
Can you just...
Okay.
Yeah. So you mentioned one condition is clock has to be a quantum system. Can you elaborate?
The clock is a quantum system if you believe the quantum mechanics is universal. Not it has to be. I would prefer if it was not. It would be easier to deal with it. But then I cannot also claim that it's a physical degree of freedom in nature.
Okay, so a phone is a clock, right? I mean,
A phone is pretty
because
quantum
it is
in
a
many
quantum
ways.
system in some, okay.
You are a quantum system, by the way, according to quantum mechanics, but we deal with you luckily in a semi-classical approximation, and that works.
Yes.
So
sorry.
yes. Then I was just going to say, then I don't see where in these conditions you stated makes a physical object a clock rather than something else. Like what's specific about clocks?
Okay, in specific models, in specific contexts, I can list what are the properties that are required for that step of inverting for a time coordinate and then inserting into the other quantities to have a relational evolution, which are the conditions that have to be satisfied, but is a context dependent. It's not that there is absolute characterization of what a clock should be. I mean, it has to be monotonic, appropriate, at least locally, and for a
So you
subset
don't
of
need
its
to have
values.
like some kind of internal
Sorry?
rigidity, like some kind of rigidity or like some kind of periodicity or
I'm not sure what you mean by that.
Like usually we think of physical clocks as something periodic. I mean, that's
Well, if
You
something
see,
is
like,
very
it's very-
periodic, we will only measure cycles of time and not time evolution. But luckily,
Yeah.
it's not really periodic.
But it
It's
has to
periodic,
be-
and then we say 1 more minute has passed, 2 minutes, 3 minutes. So there's
and then of course you can.
it's periodic in a subset of the story. Then
But what I mean by periodic is something that does not just degenerate in the outside, or like it has some kind of internal equilibrium or
some
something like
regularity.
this. Yeah, some regularity.
not cyclicity. I mean,
Yeah,
of course. I mean, as I said, a good clock has to behave nicely enough that you can rely on it to label time evolution. For example, if I'm now serious about the quantum nature of my scalar field, and then I have to revise all of that in the quantum domain, then I have to pick up some states on my clock, because my clock is going to be in one state or another. If I pick up a state which is highly quantum, with huge quantum fluctuations in the value of the clock, well, I can still try to use it as a clock, but it's a terrible clock. I'm already Italian, so I already get late to appointments. if I start to use a highly quantum clock, I lose all my friends.
Richard, last question.
Thank you. Yeah, it's a very general question on your use of seeds of space-time.
Mm-hmm.
So in principle, I think there could be two ways of using it. One is just to use it as rephrasing the problem, saying that we have emergence of space-time, so we want to understand it based on the fundamental theory, and whatever is the way of understanding it based on the fundamental theory indicates, in some sense, in very broad sense, the seeds of space-time. Or you might have a more.
So far, I think I agree.
Okay, so that okay. So
Now
that
tell me the alternative. Maybe I agree more
there
with
might
the
be,
other.
there might be another way of viewing it, where you have a more constrained concept of seeds of space-time that might actually fade, where you might say, okay, there is emergence of space-time, but in the end, it turns out that there are no seeds of space-time along the lines.
Okay, but these two things are not alternative, really.
Find it. So I mean, I think
No, they're not alternative. I mean, I agree with both. It's not contradictory. The point is that in your first characterization, you define as, without any additional condition, you define a seed of space-time, whatever in some sense originates upon emergence process space-time as we know it.
right.
Okay, and I'm fine with that. That's a seed. Now you can tell me, okay, but we can refine the notion of seeds. There may be additional conditions. And we impose them in a particular model, and we simply do not find them. There's no such thing satisfying all those conditions
Right.
that also leads to the emergence of space-time. Then I would say, well, that was a nice guess for what the characterization of seeds would be, but it fails. It's good, it's bad. From a physics point of view, it doesn't work. And so I would still say it has to work as a necessary condition for actually being recognized as a seed of space-time. Then it's not sufficient because I may need additional conditions, but it still has to work.
All right. So you do have the first concept of seeds.
I think so to start with. I mean, I can love whatever fundamental degrees of freedom I want, and I may say, oh, you see, they already have these properties that I think they're good, the seeds of space-time, and then the emergent thing doesn't work. My effective cosmological dynamics is not corroborated by experiments and observations. Well, the theory fails, so whatever was my initial seed, either I have to modify it or I have to modify something else in the process, but I cannot take it as to be the seed of space-time.
I have a very brief follow-up on that. So I completely
In your
agree
quality
with
as a
that
child.
use of of seeds for the emergence of space-time. So there must be seeds of space-time in some sense at the fundamental level. I think it's very confusing, at least to me, to use the same locution when you talk about laws, because presumably laws are not just seeded at the fundamental level and then emerge at an effective level in some sense or other, but rather you would want to have an analysis of laws which is also valid fully, without just being seeds, but full blossoms, I guess, or, already at the fundamental level.
Okay, let me put it like that. First of all, just for being honest, I would not subscribe neither to the humanist, Humean notion of laws nor the primitivism.
Without any specific
So
analysis, but it seems like there should be laws.
So okay, let me clarify the logic there. There is a certain way of characterizing what a law is, be that human or primitivism or whatever. There is a certain definition of what a law is. Now, normally that would require space-time, that would rely on space-time. Now I'm saying, well, can I broaden or weaken or that definition to rely on something else, which is not space-time, but I can see in my fundamental structures? Call it as you like. In that sense, if I do that, if this is successful, then laws will be there. They will be at the fundamental level. They will not need space-time by construction. It's exactly the purpose. To have them not emergent, not relying on space-time, they are there. Then the rest is language. Call them as you like, but they are there. That was exactly the goal. My statement is there are some features of my fundamental entities in these models that I can propose at least as ground enough for laws in a certain sense. For laws there.
I completely, I think, understand that, and that's why I think that the locution seeds of laws is
no, these are, these are the seeds of space-time and also seeds of laws the way we understand them, which is based on space-time.
Yeah, okay.
That's what it was meant.
Anyway, thank you very much.